And so first up we have Savannah from the University of Alabama talking about the who/why big team science.
I have to have a good security blanket, and this thing's not tall enough for me, so sorry. All right. First, I want to say thank you to AIMOS for the scholarship, as well as providing travel funds so that I could be here, because it is a large and long travel from the United States. So I wanted to say thank you. Today, we're going to talk about who and why do people do big team science. So we're specifically talking about individuals that do big team science projects. Today's agenda, because every good project starts with agenda, is we're going to do a little bit of background. I don't want to get too much into it because most of you should have a good amount of background. And then we'll go into the current state of big team science, which is often abbreviated as BTS. So when you see that, that's what that means. And then we'll do a future directions / current project that I'm proposing. So we'll do, original background is that we have a replication crisis in psychology and a lot of fields. Well, from that, a lot of movements come out of it. And so we have several movements happening at the same time. One of them is the credibility movement, which is going by Sabine. And then we also have the open science movement. And that is mostly focused on open science practices. We also, at the same time, have a big team science movement. And what a big team science means is it's a large group of people doing science, specifically collaborations between people all over the world. So this should be diverse populations that are allowing us to bring in diverse ideas and perspectives into our projects, which in turn will allow us to have more generalizability and reliability in our research processes. There is no definition technically of big team science. So myself and Dr. Anne Buchanan have decided to come up with one. It's completely arbitrary. So we have decided that big team science will be defined for this project and the project that's after this first project as 10 or more authors from 10 different affiliations or different institutions. And we chose 10 just because some small team science like that is a really large number, especially when you have the institution aspects, but also to people that do big team science, that feels really small. So it's arbitrary. And anecdotally, what big team science is it's not determined, and there isn't really research in what big team science is. And so a lot of people continue to say early career researchers typically are the people that are doing the movements happening to get over the replication crisis or reproducibility movement. But there's no research out there showing that to be actually true or false. And so the other thing is there's a potential that there's some lack of investigation just because a lot of research fields, big team science is newer. Obviously that's not the case in all because physics has been doing this for a hot minute. And so specifically I come from a psychology background, and so when you look at the open science collaboration, that was in 2015, not even 10 years ago. And so a lot of this research on big team science has not really been done. So why do we choose to study big team science? I like to take things back to their roots. Big team science typically, a lot of the papers that come out of big team science and the research that's been done on big team science is typically about challenges, lessons learned, or why we should be doing big team science, but no really information is done about who is doing it and how do they benefit, who is benefiting from it, and isn't actually doing anything for the current state of the field. These are questions that have not been asked. On the other side, because we also have a why, yes, we really don't know why people take place. And so there's one other person that I know of that has done a study on why people do big team science. And so the project that I'm proposing adds on to that. And we'll talk about that in a later part of this presentation. And so for who does big team science, we'll start with this project first. We had 4 research questions, and so the first are, what are the publication sources? What types of things are being published? Is a big team science publication? Who exactly is involved? So like, where are you from? Those kinds of questions. What's your age? And then how is diversity changing or evolving in big team science over time? If you want to read the full paper, the OSF has our preprint on that. But I'll go over some of the results that specifically focus on who and is diversity changing. And so this project was done with 500,000 articles through Elsevier's database and over 3 million unique authors. So it's a pretty good database, a large number of participants. And so this first graph is showing you big team science articles across time. And so the bottom axis, you can see that that's publication year from 1970 until now. And then the number of articles per year. And so each color is also represented by a different subject area. And so we divided them into like 4 main subject areas. So red is health science, orange is life science, green is physical science, and blue is social science. And so you can see that across time, the number of big team science articles are actually expanding. Again, big team science is 10 people at 10 different institutions. We also see that seniority, so this is about career length, so that it's again over time. So year of publication is on the x-axis, and average career length, which is defined by your first publication to now, is on the y-axis. And so over time, you start to see that, in fact, our career lengths and the age of our people publishing in big team science are actually decreasing. So this is definitely proof that, in fact, the movement is run by early career researchers, so go us. And so that's a really cool finding that we have. And then this one is a little complicated, so I'll walk you through it. So the top is big team science publications, and the bottom is all publications in the Elsevier database. Each of them are color-coded by how many articles there are in that block. And so you can see that when you just look solely at it, the United States is definitely running this pretty hard. And that is true for both big team science and all publications. But you start to see a little bit of change happening between all publications and big team science publications. And so in all publications, the top 2 are, North America and Asia. And then for big team science, it's still North America. But now we have Western Europe happening. And so each of these blocks, I'm going to walk up here and I'll try to speak loud. Each of these blocks are designed by sub-region. And so it goes like this from smallest, so the smallest being that top corner. Obviously, we're still not really diverse. We do see some diversity happening, which is exciting, but we still have a lot of work to go, considering the US is dominating. And so, yeah, the conclusion of this first study is that we're still very much big team science publications are still very much run by early career researchers, so we do have proof of that now. And we're still weird, so Western, educated, industrialized, rich, and democratic geopolitical regions, with health and physical science typically accounting for the majority of big team science articles. But we also do see some trends happening to show that we're doing something. So I'm a big team science person, so I'll tell you that as a conflict of interest, I guess. So the increase in preprints across time does show we are in fact doing some open science practices We do have more articles across time happening, although not enough happening. And we do start to see more non-weird authors happening in first author versus other author, as well as just in general being on papers. So then we're going to talk about this other project, which is why do people do big team science, the expectations of researchers in open science collaboration. Again, OSF is linked. I have 3 research questions for this, which are what do collaborators want from big team science, like what aspects are the most important? What are big team science organizations or projects meeting those expectations? Because I think that's a really important question. And how do we get people to do more big team science? So this project is very much still in data collection stage. And so I wanted to give you an idea of what the factors we are looking at. And so there are 5 different categories we're going over. And so the first one is career advancement. And this is like things like, I wanted to get authorship. I needed a letter of recommendation, those kinds of things. Learning experiences is like, I needed to improve my open science skills. I needed to improve my research skills. And so they're answering how important each of these aspects are to them at the beginning of a big team science project. And then mentoring, which used to be called teaching, but because it's not quite inclusive, is now called mentoring. And these are things like a decreased amount of time to help onboard students. Tangible was like, did you get course credit or actual payment? And then intrinsic is, did you want to make an impact on the field or the world? And then they also will answer the same questions, but to see if the project met their expectations. And so they will answer another Likert scale that says like, I did gain this or I didn't gain this. And then the same questions, just formed in past tense. But most of you maybe have done some big team science and would maybe like to help a girl out. So if you want to participate and you've done some kind of big team science, again, that's 10 authors at 10 different institutions. You can go to the Form R link, which is the one on left-hand side. Or if you just want to take a look at what the project is, you can go to the one on the right-hand side. If you don't want to do that now, you can go to the links. The first one is just like how to test it, and then the second one is the actual link itself. And that's all I had.
Hello everyone, my name is Robin. I am a medical resident in dermatology and also a PhD student in epidemiology and public health. I am very glad to be able to give this talk today, and I would like to thank the AIMOS community for giving the opportunity for me to present my research project, even though I would have liked to be here to present it physically. However, I will be giving this speech remotely from Paris from this recorded session. So I will be presenting my research project, which is an overview of the redundancy and the factors of variability of the overlapping systematic reviews with network meta-analysis evaluating the efficacy and safety of systemic treatments in psoriasis and other immune-mediated inflammatory diseases. I hope this speech will clarify this very long title. My research project mainly focuses on psoriasis, which is a frequent and chronic inflammatory skin disease that can have an important impact on people's health and quality of life. For the more disabling forms of psoriasis, many oral or intravenous drugs are available, thanks in large part to the recent and rapid development of biological treatments. To be approved by drug regulatory agencies, these treatments need to be compared in randomized controlled trials against placebo to evaluate their efficacy and safety. Thus, most of the trials in psoriasis have been conducted between an active drug and placebo. But for patients and clinicians, it is particularly important to have reliable knowledge on the relative efficacy and safety between active treatments in order to guide clinical decisions. However, these direct comparisons are rare. This is where network meta-analysis can help overcome some gaps in comparative effectiveness research. So what is network meta-analysis? First of all, a meta-analysis is a method that pools the result of the trials that compare the treatment A versus the treatment B, and calculates a summary statistic of the relative efficacy or safety of treatment A versus treatment B. Network meta-analysis now is a statistical method that allows to compare several treatments in the same analysis by combining direct and indirect evidence. Direct evidence is data directly extracted from the trials that compare the treatment A versus the treatment B, and indirect evidence are mathematically deduced when two treatments A and B have both been compared to the common comparator, a treatment C. Network meta-analysis allows an estimation of the relative efficacy and safety of the treatments and allows an estimation of the ranking of these interventions given specific outcomes. Recently, due to their popularity, there has been an increase in the number of published network meta-analyses in various research fields, with many redundant publications that yield different and sometimes discordant results. The first part of my research project aimed to realize an overview of the network meta-analysis that evaluated the efficacy and safety of the systemic treatments, that means oral or intravenous drugs, in moderate to severe psoriasis. The objectives were to assess the number of redundant network meta-analyses per year, to describe their characteristics, and to compare their differences. To do so, we conducted an overview of the network meta-analysis that evaluated the efficacy or safety of the systemic treatments for patients with moderate to severe psoriasis. Our main outcome was to assess the number per year of redundant network meta-analyses and to describe their overlaps and differences. Overall, we identified 47 redundant network meta-analyses published between 2006 and early 2021. With an increase in the number of published network meta-analyses each year, starting from 1 network meta-analysis in 2006 to 12 network meta-analyses in 2020. We found that more than half were industry-funded, that most of them only included a fraction of the available treatments, and that most of them were of poor methodological quality, with few protocol registration and a focus on short-term efficacy outcomes. Also, we observed that there were some disagreements between the network meta-analysis conclusion, with industry-funded network meta-analysis almost systematically citing their own treatment as being best or among the best. We thus hypothesized that funding may have an impact on the network meta-analysis conclusions, which leads us to the second part of my thesis project. The second part of my project was to evaluate if funding had an effect on the abstract conclusion of the network meta-analysis evaluating the efficacy and safety of some of the systemic treatments in chronic inflammatory diseases. We extended our scope of interest to include diseases that shared common physiopathology and treatment options with psoriasis, which would also allow to increase our sample size. Furthermore, since there is more and more incentive to use network meta-analysis in clinical practice guidelines, one of our objectives was also to evaluate if the funding had an effect on the diffusion of network meta-analysis into clinical practice guidelines. To answer our research questions, we conducted 2 overviews. One for the network meta-analysis that evaluated targeted therapies in the diseases of interest, and one for the clinical practice guidelines published during the last 5 years concerning the therapeutic management with targeted therapies of the same diseases. Our main outcomes were to evaluate the association between funding and the number of treatments cited as best in the abstract conclusion, and the association between funding and the coherence between the abstract and the reported results. As secondary outcome, we investigated the diffusion of network meta-analysis into clinical practice guidelines given the source of funding. To evaluate whether the abstracts were coherent with the reported results, we assessed each sentence from the conclusion and verified if they were supported by the results or not. For example, if the authors claimed that a treatment was best, based on the ranking results, but without considering that the difference with the other treatments was actually not statistically significant, we will consider the conclusion incoherent. On the other hand, if all the sentences in the conclusion were supported by the results, we considered the conclusion coherent. Overall, we included 216 network meta-analyses in our review. 20% of the network meta-analyses registered a protocol, and a third were industry-funded. Half of the studies evaluated both efficacy and safety outcomes, and less than half defined a primary outcome. Regarding our first main outcome, we found that there was an association between industry funding and the citation of only one treatment as being best in the abstract. Moreover, for industry-funded network meta-analysis, when one treatment was cited as being best, it was systematically the sponsored treatment. And when several treatments were cited as being best, the sponsored treatment was almost always among the top treatments. For our second main outcome, we found a negative association between industry funding and the coherence between the abstract and the results, which means that industry-funded network meta-analyses were more likely to have incoherence between the abstract and the reported results. Overall, the main reason for incoherence was the omission of citing another treatment that was not significantly different, which was more often the case when only one treatment was cited as best. Regarding the diffusion of network meta-analysis to clinical practice guidelines, 60% of them use network meta-analysis in their body of evidence. For those who did, 40% relied on industry-funded network meta-analysis, either exclusively or in conjunction with non-industry-funded network meta-analysis. This second part confirms some of the results from our previous work, with many redundant network meta-analyses published in a short amount of time. Here, 1/3 of the included network meta-analyses were industry-funded and heavily promoted their own sponsored treatment. Even though industry-funded network meta-analyses were less likely to register a protocol or define primary outcome for their study, the proportion of network meta-analyses that did was found to be low irrespective of the study funding. We found that despite growing incentive about the use of network meta-analysis in clinical practice guidelines, only 60% of the included clinical practice guidelines relied on this type of evidence. The self-promoting aspect of industry-funded network meta-analysis on the one hand and the overall low quality of some non-industry-funded network meta-analysis on the other hand could minimize the advantages of network meta-analysis and undermine its important potential. This could also explain the reluctance of guidelines developers to include them in their body of evidence. Regarding the network meta-analysis that had conclusions that were coherent with the reported results and still provided different results from other similar network meta-analyses, an ongoing work will focus on evaluating if the differences in results could be explained by different methodological choices and inclusion criteria in the network meta-analysis. To do so, we will use the data from the latest Cochrane network meta-analysis evaluating the systemic treatments in psoriasis, and reanalyze the data using several different methodological scenarios and evaluate the change in the results and the ranking of the treatments. You will find in this slide the different references for this presentation. So that is all for this presentation. I would like to thank you all for your attention, and I would like to also thank the AIMOS community for their support for this project and also making this presentation possible. And I wish you all a very good afternoon.
Right, so most of you will be familiar with the problems of researcher degrees of freedom and the Garden of Eden files. But this is probably within the context of hypothesis testing or perhaps estimation. But these are issues in model-based research as well. And this is an approach that's routinely used in my home discipline of ecological modelling for conservation decision making. And so researcher degrees of freedom and their impacts are, I think, nicely represented in this forest plot here, which comes from our preprint of the many analysts study in ecology and evolutionary biology, where we crowdsourced almost 250 analysts to answer the same research question with the same data set. you can see that a diversity of analysis strategies resulted in variation in effect sizes and their direction. So in talking to my ecological modeller colleagues about trying to implement pre-registration for model-based research, they responded to me, but Elliot, I don't do hypothesis testing. I can't pre-register my research. They objected to pre-registration on the grounds that it didn't reflect the typical modelling decisions that they make. Their second objection was to the process of pre-registration. They felt that it conflicted with the way they do modelling. So typically modelling is done in an iterative and non-linear fashion. There are genuine decisions that are data dependent. So for example, modellers need to conduct exploratory analyses looking at the distribution of some variables, and this might in turn influence particular decisions about what model is feasible given the data. So instead of throwing the baby out with the bathwater, I propose what I call adaptive pre-registration. So the first part of this research is about devising a strategy for expanding pre-registration to model-based research contexts. So adaptive pre-registration can account for the iterative nature of model development. The second part of this research develops a template for pre-registration that can be used for modelling as it's done in ecology and pre-registration. And finally, I test and evaluate both the adaptive pre-registration methodology and the template using a real-world case study of environmental flows modelling. I'm not going to talk about the last two components here. I'm just going to focus on this first one, adaptive pre-registration. So there are two key features of adaptive pre-registration. The first being the ability to register flexibility. So this is where a modeller might specify in a particular pre-registration item a decision tree or some other heuristic that links a specified analysis to particular outcomes from that analysis and how these might trigger particular decisions. The second feature of adaptive pre-registration is the use of interim pre-registration. So as the modeller proceeds through the modelling process from model development, testing and evaluation, they also cycle through this process of ideation, pre-registration, execution of that pre-registered analysis plan, and back again, generating interim pre-registrations as they go along. But what platform or tool exists to be able to implement this? Well, modelers often use GitHub in their research workflows already, and it's got some nice features that we can leverage. So here's an overview of the entire process. I'm not going to go into it in any particular detail, but if you'd like to see a step-by-step guide, I've made a website over here that you can check out. So the idea is that on GitHub, where the data and the code is stored, the pre-registration document is also located. And this document is version controlled. Changes to the pre-registration are tracked throughout time. We can also leverage semantic versioning and GitHub's releases and tagging features. So this is particularly useful for when we want to record the outcomes of these registered flexible analyses. So how releases work on GitHub is that it takes a snapshot of the repository at that particular moment in time, archiving the entire contents of the repository. And the third feature that we can leverage is GitHub issues. So for each item in the pre-registration document, we can create a GitHub issue and then describe the analysis that is being undertaken. That link is then recorded in the pre-registration document. When we work in GitHub and we're making changes, we're conducting our analyses, we make commits, and we can tag that particular issue. So any work going towards that particular pre-registration item is captured in one location. Researchers can also have conversations there, and so that whole decision-making process is made transparent. We can see the specified analysis that was made in the pre-registration. We can see what was done. Then we can see the results of that analysis. Then we can see the particular modelling decisions that were made based on the results of those analyses. Anyway, yeah, just thank you. Oh, yes, that's one. Thank you. So here's a snapshot of part of the pre-registration template that I've come up with. This was based on a series of workshops that I conducted with real modelers doing applied ecology. Again, you can check it out at this link. And finally, I just want to end by spruiking this pre-registration working group that the Centre of Open Science has come up with. Myself, Fiona Fiddler, and a bunch of others are on this working group. And our aim is to curate and evaluate pre-registration templates. So if you've been working on your own template for your particular methodology or field that you feel is not represented by existing templates, please send that along to us or get in touch if you feel that you need a template for your work. So I'll end it there. Thank you for listening.
Thank you. We're going to be well under schedule, so if you do have any questions, think of them now. But we have finally a pre-recorded talk from Ben McGredlian at Cardiff University talking about registered reports community feedback.
Hello, I'm Ben McGredlian, and I'll be speaking to you about my PhD project titled Registered Reports Community Feedback, a website for collecting peer review experiences from authors and reviewers. I'm based at Cardiff University in the United Kingdom, and I'm supervised by Chris Chambers and Savannah. I'm funded by the AIMOS Foundation. Okay, so here's an overview of what I'm going to speak about over the next 10 or 15 minutes. Firstly, for those unaware, I'll briefly describe registered reports along with some current evidence and gaps therein. Then, relating to this project, I'll outline some example research questions and a methodology. And finally, I'll give you a live demo of the project website before outlining next steps. So, what are registered reports? Well, to understand registered reports, we first have to outline traditional peer review. In traditional peer review, all steps of a study, from its inception to writing up, occur before peer review. Then, typically after a number of rounds of peer review, the article is published. By contrast, registered reports are a publishing format that combines additional peer review of a study proposal before results are known. This study proposal would include the hypotheses, methods, and planned analyses. At this first stage, reviewers assess the importance of the research questions and the rigour of the study methodology. This means that any problems with the study can be identified and improved before data is collected or analyses are conducted. If the study passes its first peer review, it is given in-principle acceptance. This means the journal agrees to publish the completed study on the basis of its research question and the methodological rigour, irrespective of the results found, as long as the study is conducted as initially planned. And this is checked by peer reviewers at a second stage. With this in-principle acceptance in hand, researchers can then go and conduct their study. After writing up the study, authors return for the second stage of peer review. And as mentioned, at this second stage, reviewers assess the completed manuscript's compliance with the original study protocol and whether the conclusions are based on a sensible interpretation of the findings, i.e. the conclusions don't over or understate claims made based on inferential statistics, etc. Once reviewers at the second stage are satisfied, the manuscript is published, and importantly, although registered reports are designed primarily for confirmatory research with stated hypotheses, the format is flexible and allows for exploratory results to also be reported as long as they're labelled as such. So, briefly, and I'm sure most of you are aware, registered reports are one solution to address the replication crisis and irreducibility. The replication crisis has been defined as a crisis of confidence in science, reflecting an unprecedented level of doubt among practitioners about the reliability of research findings in the field. Known fields impacted include psychology, medicine and economics, and irreducibility of findings has been perpetuated by a combination of systemic factors, for example, incentive structures in academia, publishing and industry, and individual factors such as questionable research practices and publication bias. As an example, in psychology, large-scale replication projects have shown reduced significant findings and reduced effect sizes across well-known articles and journals. And a lack of reproducibility has enormous consequences for the field. For example, it's estimated that 50% of preclinical research is not replicable, with a related cost of approximately $28 billion. In addition, the number of positive results in the literature has been increasing over time, many of them likely false positives. And certain fields, for example psychology, have relatively immature theory development, which, along with many false positives, will harm theory prediction and development. One solution to irreducibility is standard pre-registration, which is currently in use across fields. Standard pre-registration usually involves making the study protocol public before the study is conducted. In theory, this helps to guard against questionable research practices, such as hypothesizing after results are known, and publication bias. However, the initial protocols are not peer-reviewed, and there is typically no obligation for reviewers to compare those against the study manuscript, and reviewers often don't. There's also mixed evidence about how well standard pre-registration guards against questionable research practices and publication bias. It may be somewhat useful, but it doesn't provide a strong control against such practices. So, compared to standard pre-registration, registered reports is therefore a stronger antidote to the replication crisis. In summary, it has the following advantages. For the scientific community, it offers rigorous review of theory and methods. It strongly reduces, or maybe even eliminates, publication bias, reporting bias, and questionable research practices. And for authors, it provides peer review when it is most helpful, and publication guaranteed, regardless of the results found. Okay, so now I'll give a brief summary of the evidence relating to registered reports. There are over 330 journals offering registered reports as a format, with over 650 published articles, and many more in the process of collecting data having received in-principle acceptance. Now I'm going to show you a few findings from recent years. These two graphs on the left show that registered reports have far more null findings compared to the traditional literature. And the right-hand graph shows that, compared to traditional manuscripts, registered reports were rated higher across a range of quality criteria, including the rigour of methods and analysis. Despite what we do know, our understanding of registered reports in several key areas is limited. This includes how well the process of registered reports peer review is implemented in journals and where in the process issues exist, and how the process differs for different groups based on aspects of power and diversity. If we can understand these areas better, we can improve how registered reports are implemented across journals. This might lead to better and more equitable experiences for researchers, reviewers and editors, and to a more favourable view of registered reports, and in turn we hope this will lead to increased uptake of registered reports and ultimately contribute to an increase in research quality. To shed light on these gaps in the evidence, I'm going to share some example research questions for our project. A few example research questions include: which journals or platforms have the highest and lowest speed and quality ratings? Are speed and quality positively or negatively correlated across journals? What factors impact authors' positive or negative experiences of registered reports? And how does this vary by gender, ethnicity, and career level? To what extent do journals adhere to their policies, regardless of manuscript outcome? And do authors report that reviewers exert undue power over the review process? To address these research questions and others, I will outline the methods of the project. The design of the study is an online survey, collecting quantitative and qualitative data. measures were custom made by the research team. Participants were asked to rate up to 70 items regarding various aspects of their experience of the registered reports peer review process. They were also invited to provide free text responses for each item. We recruited participants in a number of ways, primarily by obtaining the corresponding author details of published registered reports manuscripts, along with standard recruitment routes. A custom website was built to host the survey, and this allowed for live dashboards, user login, and an invite system. So now I'm going to give you a quick demo of the live website to show how responses are captured and how summary results are displayed. Okay, so when an author or reviewer wants to give feedback on their experience of registered reports peer review, first of all they go to this page. We want to know for this experience, did they act as an author or a reviewer? And for this example, we're going to say author, from which journal, did the peer review occur at, and we're going to choose the top one. And what stage or stages do they want to give the feedback on? In this case, we'll just say stage 1. And crucially, what was the outcome of the manuscript at that stage? And we're going to say it was granted in principle acceptance and proceeded to stage 2. We're also collecting information around when it took place and the academic career status during that time. And finally, we ask for a reference code so they can come back to it and give additional feedback later. Okay, so now you'll see the summary. And these questions items are within the speed category. And participants are being asked to rate various aspects of the speed from 1 to 5. So we're going to choose some ratings here. And if we scroll down, we move on to the next category, which sees quality. And there are a lot of questions also with a 1 to 5 rating. But if we scroll down, you'll also see there are other question types. For example, this one here, which is asking authors to what extent did they feel that reviewers or editors were granted too much, too little, or the right amount of power to shape their study design at stage 1. And further down, you'll see there are other types of questions, for example, asking for numerical data. Hopefully that will give you a bit of a sense of the survey. There are many more questions and categories, but we only have time for a snapshot now. So I'm going to move on and show you the summary results presented in dashboard form. So here is the main dashboard showing journals and platforms. This dashboard lists all journals that have previously or currently offered the registered reports format. Some of these have not received any feedback, some have only received a small amount. We only start showing the average ratings when journals or platforms have received 5 or more pieces of feedback. So for example, if an author gives feedback for stage 1 and 2, that will count as 2 pieces of feedback. Now, if you want to, you can search by keyword. So for example, if we type the word psych, we list the only journals and platforms with the word psych in the title. We can also only show journals with 5 or more ratings like this. If you're interested in which journals seem to rate higher, you can click speed here, and now this is sorted by speed rating. So it can be done for quality. Okay, so for each of these journals and platforms, we can see more detailed summary statistics. So for example, let's take this one here, which currently is rated as the highest quality. And at the top, you can see the same averages that we just saw in the dashboard. Now, these are averages across all items in these categories, but it's quite likely that you want to see a breakdown of those. So below we have 3 different tables, showing them broken down by stage, 1 or 2, by role, author or reviewer, and then by role and stage. You can see, for example, what is the average speed rating from authors at stage 1. For anyone interested in item level data, we present them below. So for example, here are the average ratings per item in the speed category. And for other question types, we present distributions of responses as shown. I hope this has been a helpful overview despite being brief. The site is now live, so if you'd like to look at the summary data or contribute to it, you can visit it at registeredreports.cardiff.ac.uk. Finally, what is next? Well, I'll be moving on to analyses, including inferential statistics, and eventually I'll share the project's findings. I'm also currently collecting data for a related project. I'll use this opportunity to advertise this since you are a community we'd like to hear from. In brief, we're conducting a global survey exploring the extent to which the results of a research study influence publication in the peer-reviewed literature. And the broad aim is to build a better picture of factors influencing peer-reviewed publication across different academic fields. So it takes 5 to 10 minutes to complete. You can visit the link shown here to participate anonymously, and that is benmeg.com/results. I'd like to finish by thanking all of those who have made this project possible, or who have supported my work as a PhD student. This includes the University of Cardiff, my funder, the Arnold Foundation, my research team, colleagues who helped test and pilot the feedback website, and all the participants who contributed their time and effort to this study. Lastly, I'd like to thank AIMOS for their 2022 top-up scholarship, and all those listening today for your time and attention. We're all keen to hear from those interested in our work. If you have any comments or thoughts, please do feel free to get in touch by emailing me at benmeg@benmeg.com. And these slides are also available on my website, and a link to that is benmeg.com/slides. Thank you again, and I hope you enjoy the rest of the conference.